What if everything we thought we knew about the universe was just the tip of the iceberg? Picture standing at the edge of cosmic understanding, peering into the abyss where the rules of reality seem to twist and warp in ways that defy logic. This isn't science fiction, it's the startling truth hidden in the depths of space, where galaxies move in ways they shouldn't, where light bends in impossible patterns, and where the very laws of physics seem to unravel before our eyes. These aren't just minor quirks of the cosmos, they're seismic shifts in our understanding, rewriting the textbooks and forcing scientists to question the foundations of existence itself. Think about the last time you looked up at the night sky and felt that awe, the sheer vastness of it all, the mysteries waiting to be uncovered. Now imagine discovering that some of those twinkling lights aren't just distant suns but cosmic anomalies, behaving in ways that shouldn't be possible. Take Einstein's theory of relativity, for example, a cornerstone of modern physics, tested and proven time and again. But what happens when we stumble upon phenomena that even Einstein couldn't have predicted? Unexplained galactic rotations, particles moving faster than light, regions of space where gravity seems to vanish entirely. These aren't plot holes in a sci-fi story. They're real, documented observations that have left even the brightest minds scratching their heads. That's where this journey begins. Over the next 30 revelations, we'll explore the most obscure, mind-bending discoveries in cosmology, each one a puzzle piece in a grander mystery. These aren't just academic curiosities, they're glimpses into a universe far stranger and more magnificent than we ever imagined. And here's the thing, you don't need a degree in astrophysics to appreciate the wonder of it all. Whether you're a seasoned space enthusiast or someone who's just starting to gaze up at the stars with curiosity, these discoveries will change how you see the cosmos. So buckle up, we're about to dive into the anomalies that reshaped reality as we know it, and by the end, you might just find yourself seeing the universe in a whole new light. Let's start with one of the most baffling cosmic mysteries, the Pioneer Anomaly. Back in the 1980s, NASA's twin Pioneer spacecraft, drifting toward the edge of our solar system, began doing something impossible. According to Newton's laws of motion, these probes should have maintained a steady speed as they journeyed through the void. Instead, they inexplicably slowed down as if something, or some invisible force, was tugging them backward. At first, scientists assumed it was just a technical glitch, maybe residual fuel leaking from the probes, or even heat radiating unevenly off their surfaces. But after years of painstaking analysis, none of those explanations held up. The slowdown was real, measurable, and utterly perplexing. This wasn't some minor discrepancy. The Pioneer Anomaly forced physicists to confront a startling possibility. What if our understanding of gravity was incomplete? Einstein's theory of general relativity had redefined gravity as the curvature of spacetime, and for decades it passed every test with flying colors. Yet here was a phenomenon that didn't fit. Some researchers speculated it could be evidence of dark matter, an invisible, mysterious substance thought to make up most of the universe's mass exerting an unseen pull. Others wondered if entirely new laws of physics were at play, hidden in the depths of space where human probes had never ventured before. The strangest part. The anomaly wasn't limited to the pioneers. Later missions like the Galileo spacecraft bound for Jupiter showed similar unexplained behavior. It was as if the universe itself had a hidden rulebook, one that only revealed itself at the fringes of our exploration. Even today, decades after the initial discovery, no definitive answer exists. The Pioneer Anomaly remains an open question, a ghost in the cosmic machine that continues to whisper. What if we've been missing something fundamental all along? This isn't just about a couple of old spacecraft acting oddly. It's a reminder that the universe loves to surprise us. Every time we think we've figured it out, something like the Pioneer Anomaly comes along and pulls the rug out from under our feet. And that's what makes cosmology so thrilling, not the answers we have, but the mysteries that keep us searching. Now let's turn our attention to another cosmic conundrum that shattered expectations, the mystery of galaxy rotation curves. In the 1970s, astronomer Vera Rubin made a discovery so baffling it upended our understanding of how galaxies work. She focused on spiral galaxies, those majestic pinwheels of stars, expecting their outer edges to behave like planets in our solar system, slower moving the farther they were from the center. After all, Newton's laws told us gravity weakens with distance, so stars on the outskirts should orbit more sluggishly than those near the galactic core. But Rubin's observations revealed something astonishing. Stars at the very edges of these galaxies were whipping around just as fast as those close in, as if some unseen hand was propping them up, defying the pull of visible matter. This wasn't a minor discrepancy. It was a full-blown revolt against the laws of physics as we knew them. If Newton's and Einstein's equations held true, these galaxies should have torn themselves apart from the sheer speed of their outer stars. Yet there they were, spinning smoothly, their stars clinging to orbits that should have been impossible. The only explanation, something invisible, something we couldn't see or detect directly, was exerting an enormous gravitational grip on those stars. This invisible something came to be known as dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet makes up an estimated 85% of the universe's total mass. Think about that for a moment. Everything we can see, all the stars, planets, nebulas, and galaxies, accounts for just 15% of the universe's matter. The rest is this shadowy enigma, woven through the cosmos like an unseen scaffold, holding galaxies together with its gravitational glue. But here's the kicker: despite decades of searching, we still don't know what dark matter actually is. Is it a sea of undiscovered particles left over from the Big Bang? Could it be primordial black holes peppered throughout space? Or is it something even stranger, something our current physics can't yet describe? The implications are staggering. If dark matter exists, and the evidence is overwhelming that it does, it means we've been interpreting the universe through a keyhole, missing the vast majority of its structure. And yet, for all its dominance, dark matter remains elusive. Experiments deep underground, in particle colliders, and even in space have hunted for traces of it, coming up empty-handed time and again. Some scientists have even proposed radical alternatives, like tweaking the laws of gravity itself, to explain Rubin's observations without invoking dark matter at all. But so far, none of these theories have matched the mountain of evidence pointing to dark matter's existence. What makes this mystery so thrilling isn't just the unanswered questions, it's the sheer audacity of the universe to hide its secrets in plain sight. We're surrounded by this invisible architecture, this cosmic dark matter scaffolding, and yet it slips through our fingers every time we try to grasp it. Vera Rubin's discovery didn't just add a new chapter to astrophysics, it tore the textbook wide open, revealing how much we still have to learn. And that's the beauty of cosmology. Every answer leads to deeper questions. Every discovery peels back another layer of the universe's endless mystery. Just when we thought the universe couldn't get any stranger, along came the axis of evil, a name that sounds like it's straight out of a cosmic thriller, but in reality, it's one of the most unsettling discoveries in modern cosmology. Picture this: the cosmic microwave background, that faint afterglow of the Big Bang, is supposed to be the ultimate snapshot of a uniform, predictable universe. According to the cosmological principle, a cornerstone of how we understand space, the cosmos should look the same in every direction, no matter where you're standing. But when scientists mapped the CMB with unprecedented precision, they stumbled upon something that sent chills down their spines. The universe, it turns out, might have a preferred direction, a bizarre alignment of hot and cold spots that defies everything we thought we knew about cosmic symmetry. This isn't just a minor statistical quirk. The so-called axis of evil, dramatically named for how it undermines our most basic assumptions, points to a universe that isn't as random as we believe. Imagine tossing a handful of confetti into the air, only to watch it arrange itself into a perfect line instead of scattering chaotically. That's the level of weirdness we're dealing with here. Some researchers dismissed it as a fluke, a trick of the data. But the more we looked, the more the anomaly persisted, showing up in multiple independent observations. If this alignment is real, it suggests something profound. The universe might have a hidden structure, a cosmic fingerprint left by forces we don't yet understand. What could possibly cause such a tilt in the fabric of reality? One theory points to the gravitational influence of other universes, yes, other universes tugging at ours from beyond the observable cosmos. In the multiverse hypothesis, our universe might be just one bubble in an infinite froth of realities, and their collective gravity could be warping space in ways that leave traces in the CMB. Others propose that the axis of evil is evidence of a primordial magnetic field, woven into the universe in its earliest moments, or even a sign that Einstein's relativity breaks down on the largest scales. The most unsettling possibility, that we're seeing the remnants of something before the Big Bang, a shadow of a previous cosmic cycle imprinted on our own. But here's the twist. The axis of evil isn't just a challenge to theorists, it's a direct affront to the cosmological principle. The idea that the universe has no center, no edge, and no special direction. If this alignment holds up, it means the universe isn't as homogeneous as we thought. It's like spending your whole life believing the ocean is the same everywhere, only to discover one day that all the currents secretly flow in unison. The implications ripple across astronomy, forcing us to reconsider everything from the distribution of galaxies to the very nature of inflation, the rapid expansion thought to have shaped the early cosmos. What makes this discovery so gripping isn't just the science, it's the sheer audacity of the universe to keep surprising us. Every time we think we've nailed down the rules, something like the axis of evil comes along and whispers, "You're missing the bigger picture." Whether it's a statistical ghost or a genuine cosmic conspiracy, one thing's certain: the universe still has secrets we've only begun to unravel, and that's what makes the hunt so exhilarating. The moment we stop being surprised is the moment we stop learning. Deep in the void of space, beyond the glittering disk of our Milky Way, something enormous is pulling at us. And not just us, but entire galaxies, thousands of them, racing toward a point in the cosmos we can't even see. This is the Great Attractor, one of the most baffling gravitational mysteries in the universe. Hidden behind thick curtains of interstellar dust and stars, this invisible force tugs at everything in our galactic neighborhood, bending the motion of galaxies like a cosmic puppet master. Even stranger, we still don't fully know what it is. For decades, astronomers noticed something odd about the way galaxies in our local cluster moved. Instead of drifting apart as the universe expands, they were all streaming toward the same patch of sky, near the constellations Centaurus and Hydra. At first, scientists assumed it was just a particularly dense supercluster of galaxies, their combined gravity acting like a magnet. But when they tried to measure the mass of this region, the numbers didn't add up. The pull was far stronger than anything visible matter could explain. It was as if the universe had a hidden sinkhole, dragging everything toward it with irresistible force. Here's where things get even weirder. The Great Attractor sits in what astronomers call the zone of avoidance, an area of the sky obscured by the Milky Way's own dust and gas. Imagine trying to study a distant city while standing in the middle of a foggy forest. That's the challenge scientists face. Yet despite this cosmic blind spot, we've managed to peer through, using infrared and radio telescopes to map the unseen. What they've found is both thrilling and unsettling. The Great Attractor isn't alone. It's part of an even larger structure called the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. But even Laniakea's immense gravity can't fully account for the Great Attractor's pull. So what's really out there? Some theorists speculated could be a concentration of dark matter so vast it warps the fabric of space-time around it. Others wonder if it's the gravitational echo of something even more colossal, a structure so enormous it defies our current models of cosmology. There's even a fringe hypothesis suggesting it might be a rare cosmic defect, a kink in space left over from the Big Bang itself. Whatever the answer, the Great Attractor forces us to confront a humbling truth. We're still mapping the cosmos, and every time we think we've grasped its scale, it reveals another layer of mystery. What makes this discovery so gripping isn't just the science, it's the sheer scale of our ignorance. Here we are, on a tiny planet in an unremarkable galaxy, being pulled towards something we can't see, by forces we don't fully understand. It's a reminder that the universe is grander, stranger, and more mysterious than we could ever imagine. And that's the real magic of cosmology, not just the answers we find, but the questions we didn't even know to ask. If there's one thing scientists love, it's consistency, especially when it comes to the fundamental laws of the universe. But what happens when two of the most trusted methods for measuring the cosmos start giving wildly different answers? Enter the Hubble Tension, a cosmic clash so perplexing it sent shockwaves through the world of cosmology. On one side, we have the cosmic microwave background, that ancient afterglow of the Big Bang, whispering to us from 13.8 billion years ago. On the other, the flickering pulses of distant stars called Cepheid variables, acting as cosmic yardsticks in the relatively nearby universe. Both should agree on how fast the universe is expanding. But they don't, and the gap between them isn't just a rounding error. It's a glaring, unresolved contradiction that threatens to upend our understanding of dark energy, gravity, and the very fabric of reality. For decades, astronomers have relied on these two pillars to pin down the Hubble constant, the number that describes the universe's expansion rate. Imagine two clocks, both meticulously calibrated, one counting seconds since the dawn of time, and the other ticking in sync with the present-day cosmos. In a perfect world, they'd match, but instead, the early universe measurements taken from the CMB by missions like Planck suggest an expansion rate of about 67 kilometers per second per megaparsec. Meanwhile, observations of nearby stars and supernovas, led by teams using the Hubble Space Telescope, peg it closer to 73. That difference might sound small, but in the precise world of cosmology, it's a chasm. Statistically, the odds of this being a fluke are less than 1 in a million. So what's really going on? One possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't as constant as we thought. Maybe it's evolving, growing stronger over time, or interacting with matter in ways we haven't yet imagined. Another theory suggests the early universe briefly hosted exotic particles or forces that left a hidden fingerprint on the CMB, skewing our measurements. Then there's the radical idea that our patch of the cosmos sits in a peculiar void, a bubble of lower density that's distorting our local observations. But none of these explanations fully resolve the tension without creating new problems elsewhere in physics. The stakes couldn't be higher. If the discrepancy is real and not some systematic error, it means our standard model of cosmology, the very foundation of modern astrophysics, is missing a crucial piece. Perhaps gravity behaves differently on the largest scales, or the universe underwent a phase transition we've yet to uncover. Some theorists even speculate this could be the first hint of a deeper structure to spacetime, a wrinkle in the cosmic fabric that's been hiding in plain sight. What makes the Hubble tension so electrifying isn't just the mystery, it's the way it forces us to question everything we thought we knew. Science thrives on discord, on those moments when the data refuses to fit neatly into the boxes we've built. And right now, the universe is practically shouting at us that there's more to the story. Whether it's new physics, unseen forces, or a flaw in our methods, one thing's certain: the Hubble tension isn't just a problem to solve. It's an invitation to discover something extraordinary. Now imagine this: our entire galaxy, with its hundreds of billions of stars, might be floating inside a cosmic ghost town. A staggering emptiness so vast it defies everything we thought we knew about the universe's structure. This is the KBC Void, named after the astronomers Keenan, Barger, and Cowie, who first pieced together its unsettling scale. Stretching over 1 billion light-years across, this void isn't just a pocket of space with fewer galaxies, it's a gaping cosmic desert, far emptier than any model predicted. And here's the twist: we're right in the middle of it. For centuries, astronomers operated under the cosmological principle, the assumption that on large scales, the universe is roughly the same everywhere, no special places, no grand imbalances. But the KBC Void flips that idea on its head. If our Milky Way sits inside such an enormous underdense region, it means the cosmos might be far lumpier than we ever imagined. Picture a sponge where most of the bubbles are tiny, uniform, except for one gigantic hole, and we're sitting right inside it. That's the level of irregularity we're talking about. How did we even discover this void? It started with measurements of supernovas, those brilliant stellar explosions used as cosmic mile markers. When scientists tracked their distances and velocities, they noticed something odd. Galaxies near us seemed to be moving away faster than expected, as if pushed by some invisible force. At first, they assumed it was the pull of known superclusters like the Shapley Attractor, but the numbers didn't add up. The only explanation: we're not just being pulled, we're also being pushed, because the void around us lacks the gravity to hold things together. It's like being in a valley while the rest of the universe sits on higher ground, and the emptiness itself is shoving us outward. The implications are profound. If the KBC Void is real, it could solve some cosmic puzzles like the Hubble tension we discussed earlier. A local void would mean our measurements of the universe's expansion rate are skewed, because we're observing it from inside a gravitational anomaly. But it also raises thornier questions. How did such a colossal void form? Why is it centered on us? Is it a statistical fluke or evidence of a deeper asymmetry in the universe's birth? Some theorists suggest it might be a remnant of an ancient quantum fluctuation, frozen into the fabric of space during inflation. Others wonder if it's a sign of exotic physics, like dark energy interacting with matter in ways we haven't yet imagined. But here's the real kicker. If we're truly inside a void, it means our view of the cosmos is fundamentally distorted. We're like deep-sea creatures in a trench, peering up at an ocean we can't fully grasp. The galaxies we see might not be representative of the universe at large, and our cosmic senses could be missing the bigger picture. It's a humbling thought that even after centuries of stargazing, we might still be prisoners of our own celestial neighborhood, trying to map the universe from inside a bubble. What makes the KBC Void so fascinating isn't just its size or its defiance of expectations. It's the way it forces us to question our place in the cosmos. Are we special or just lucky? Is the universe truly uniform, or are we living in a cosmic anomaly? Every time we think we've got the answers, the universe reminds us how much we still have to learn. And that's the thrill of discovery, not just finding solutions, but embracing the mysteries that keep us searching. One moment, the cosmos is silent. Then, without warning, a burst of radio waves brighter than 1 billion suns erupts across the universe, vanishing almost as quickly as it appeared. These are fast radio bursts, or FRB, some of the most enigmatic signals ever detected. Lasting just milliseconds, they pack more energy than our sun emits in days, yet their origins remain shrouded in mystery. The first FRB was discovered in 2007, buried in old telescope data, and for years astronomers debated whether it was even real. Now we've detected hundreds, with some repeating in bizarre, unpredictable patterns, like cosmic drumbeats echoing from the void. What makes FRBs so baffling isn't just their power, it's their sheer unpredictability. Most come from galaxies billions of light years away, flickering into existence just once, never to be seen again. But a handful defy the rules, repeating at intervals that range from frantic to leisurely. Take FRB 121102, the first repeater ever found. It fires off bursts like clockwork, flaring for days before falling silent for months. Then there's FRB 180916, which pulses every 16 days like a celestial metronome. These patterns aren't just curiosities, they're clues, hinting at environments so extreme they warp the very laws of physics. So what's blasting these signals across the cosmos? The leading suspect is magnetars, hyper-dense neutron stars with magnetic fields so intense they could strip atoms apart. Picture a stellar corpse spinning furiously, its crust cracking under unimaginable strain, releasing bursts of energy like cosmic lightning. But not all FRBs fit this mold. Some are too powerful, too frequent, or come from regions with no known magnetars. Could they be colliding black holes? Rogue asteroids smashing into neutron stars, or dare we say it something more artificial? The speculation isn't as far-fetched as it sounds. In 1967, astronomers detected a pulsing radio signal so regular they jokingly labeled it LGM-1, short for Little Green Men. It turned out to be the first pulsar, a natural phenomenon. Yet the allure of FRBs as potential alien beacons persists, especially with signals like the WOW signal still unexplained. Scientists remain skeptical, but the possibility lingers like a tantalizing subplot in a cosmic detective novel. Even stranger, some FRBs arrive with a twist. Their waves are twisted, a phenomenon called Faraday rotation, suggesting they've traversed incredibly turbulent magnetic fields. It's as if these bursts are cosmic breadcrumbs carrying encrypted messages about the environments they've traveled through. By studying them, we've even uncovered missing matter, gas so diffuse it's invisible to telescopes, yet revealed by the way FRBs slow down as they pass through it. The deeper we dig, the more questions arise. Why do some FRBs repeat while others vanish forever? What could generate such staggering energy in milliseconds? And could these bursts be tools helping us map the universe's hidden scaffolding? For now, FRBs remain one of astronomy's most electrifying puzzles, a reminder that the universe is still writing its strangest stories, and we've only just begun to read them. The universe is a master chemist, forging elements in the fires of the Big Bang and the hearts of stars, except when it comes to lithium. Here's the puzzle. According to our most precise calculations, the early cosmos should have produced 3 times more lithium than we actually see. This isn't a minor accounting error. It's a glaring mismatch between theory and observation, one that's persisted for decades. The Big Bang nucleosynthesis, that fleeting moment when the universe was just minutes old, fused hydrogen into helium and trace amounts of lithium and beryllium. Every other element's abundance aligns beautifully with predictions except lithium. It's as if the cosmos misplaced an entire ingredient, and scientists are still scrambling to find where it went. One leading theory points to stars as the culprits. As these cosmic furnaces burn, they can destroy lithium by fusing it into heavier elements or mixing it into their cores where it's no longer visible. But here's the catch: even after accounting for stellar processes, the numbers still don't add up. Some lithium is definitely being destroyed, but not nearly enough to explain the staggering deficit. Could there be unknown stellar mechanisms at work, some exotic nuclear chemistry we haven't yet uncovered? Or perhaps lithium is hiding in plain sight, trapped in cosmic dust or floating in gas clouds too diffuse for our telescopes to spot. Then there's the more radical possibility that our understanding of the early universe is missing a piece. The Big Bang nucleosynthesis models rely on precise physics, from nuclear reaction rates to the density of protons and neutrons in those first explosive moments. What if an unknown particle, something beyond the standard model, was present in the primordial soup, subtly altering how lithium formed? Some theorists speculate that dark matter particles, interacting weakly with ordinary matter, could have skewed the delicate balance of element production. Others suggest the early universe might have experienced brief, violent phase transitions, warping the conditions under which lithium was created. But the most unsettling option: that we've miscalculated the nuclear physics itself. The cross-sections, the probabilities of particles interacting used in Big Bang models are based on lab experiments, and even tiny errors could cascade into massive discrepancies. Imagine baking a cake where one ingredient's measurement is slightly off. The entire recipe could fail. If our nuclear data is incomplete, it would mean rewriting not just the lithium story, but potentially other chapters of cosmic history too. What makes the lithium problem so fascinating isn't just the mystery, it's the stakes. Lithium is a cornerstone element, a relic of the universe's first moments. If we can't account for it, it hints at gaps in our understanding of everything from stellar evolution to the fundamental laws of particle physics. Every unexplained atom is a whisper from the past, a clue that the cosmos still holds secrets we've yet to unravel. And that's the beauty of cosmology. Even the smallest discrepancy can lead to the biggest breakthroughs. So while lithium might be missing from our cosmic inventory, its absence is pointing us toward discoveries we can't yet imagine. Among the faint glow of the cosmic microwave background, where the universe whispers its oldest secrets, there's a patch of sky so cold it sends shivers down the spine of modern cosmology. This is the CMB Cold Spot, a mysterious region stretching over 1 billion light-years, where temperatures dip dramatically lower than anywhere else in the afterglow of the Big Bang. At first glance, it might seem like a minor statistical blip, a cosmic typo in an otherwise uniform sea of microwaves. But the numbers don't lie. The odds of this cold spot appearing by random chance are less than 1 in 50. So what's chilling this corner of the cosmos to such extremes? One explanation is as mind-bending as it sounds. The cold spot might be a bruise left by a collision with another universe. In the multiverse theory, our cosmos is just one bubble in an infinite froth of realities, each with its own physical laws. If another universe grazed ours in the distant past, the energy of that impact could have stretched space-time in a way that left behind this eerie cold patch. It's like pressing an ice cube against a warm window. The glass cools where the contact occurred, even after the ice is gone. Supporters of this idea point to the cold spot's unusual shape. and the way its surrounding features align, as if something colossal once pushed through the fabric of our universe. But not everyone's convinced. Skeptics argue there's a more mundane, though still fascinating explanation: a cosmic void, a vast emptiness where galaxies are eerily scarce. Most voids are small, but the cold spot sits in a region where astronomers have found an unusually large underdensity of matter. If this void is real, it could act like a gravitational hill. Light traveling through it would lose energy, stretching into longer, colder wavelengths, a phenomenon known as the integrated Sachs-Wolf effect. Imagine rolling a ball up a slope. It slows down, losing kinetic energy. Photons from the CMB do the same when climbing out of a void, leaving the spot colder than its surroundings. Here's where things get complicated. The void explanation has its own problems. For one, the observed underdensity isn't nearly big enough to account for the cold spot's extreme temperature drop. It's like trying to explain a frozen lake by pointing to a puddle. Some researchers suggest the void might be part of a larger, invisible structure, its true scale hidden by the limitations of our telescopes. Others wonder if the cold spot is a rare fluke, a statistical outlier in an otherwise uniform cosmos, a cosmic roll of the dice that landed on the one unlikely outcome. But the most tantalizing possibility is that we're seeing both explanations at once. A void sitting precisely where a multiverse collision occurred, amplifying the anomaly. It's a cosmic coincidence almost too perfect to believe, yet the data refuses to rule it out. Whatever the truth, the cold spot is more than a curiosity. It's a stress test for our models of the universe. If it's a void, it challenges our understanding of large-scale structure. If it's a multiverse fingerprint, it rewrites the rules of reality itself. What makes this mystery so compelling isn't just the science, it's the sheer audacity of the questions it forces us to ask. Are we alone in the cosmos, or is our universe just one page in an infinite library? Do the laws of physics hold everywhere, or are there places where they fray at the edges? The cold spot doesn't just defy explanation, it dares us to imagine a universe stranger than we ever thought possible. And that's the thrill of discovery, not just finding answers, but learning how much we still have left to explore. We think we know the universe's ingredients: stars, galaxies, dust, and gas, but here's the shocking truth. Half of all normal matter, the stuff that makes up planets, people, and everything we can see, has been missing for decades. This isn't dark matter or some exotic substance. It's the ordinary baryonic matter that should be right in front of us. The math is undeniable. Based on the Big Bang's element production and the universe's density, we know exactly how much of this matter should exist. Yet when astronomers tally up all the visible stars, galaxies, and interstellar gas, nearly 50% is nowhere to be found. It's like baking a cake with a precise recipe, only to discover half the flour vanished before it even hit the bowl. So where did it go? The leading theory is as elegant as it is elusive. The missing matter is hiding in vast, thread-like structures called the warm-hot intergalactic medium, or WIMP. Picture an invisible spiderweb stretching between galaxies, made of superheated gas so diffuse it's nearly transparent. These filaments, heated to millions of degrees, don't glow brightly enough for our telescopes to spot directly. Instead, they reveal themselves subtly, by absorbing and distorting the light of distant quasars, those brilliant beacons powered by supermassive black holes. It's like trying to see a ghost by watching how it bends the light in a foggy room. Detecting this hidden matter is one of astronomy's greatest technical challenges. The gas is so hot and thin that it emits faint X-rays, but these signals are drowned out by brighter cosmic sources. Recent breakthroughs, though, are starting to peel back the veil. The ESA's XMM Newton telescope and NASA Chandra have glimpsed traces of oxygen and other elements in these filaments, their spectral fingerprints betraying the presence of the missing baryons. Even more promising, astronomers have used fast radio bursts, those millisecond cosmic flashes we discussed earlier, as probes. As these bursts travel through space, their waves slow slightly when passing through ionized gas, offering a way to measure the WIMP density. But here's the twist: even with these advances, the numbers still don't fully add up. The detected WIMP accounts for some of the missing matter, but not all. Could the rest be lurking in even harder-to-see forms, like ultra-diffuse clouds or rogue planets drifting between stars? Some theories suggest primordial black holes, formed in the universe's first seconds, might be soaking up a fraction. Others propose that our instruments simply aren't sensitive enough yet to catch the faintest whispers of this hidden material. What makes this mystery so thrilling isn't just the hunt, it's the humility it demands. We often picture the cosmos as a well-lit stage, with galaxies as the main actors. But in reality, we're only seeing the spotlighted areas. The missing baryons remind us that the universe is like an iceberg, with most of its bulk lurking beneath the surface of our perception. Every time we think we've mapped the cosmos, it reveals another layer of the unseen. And that's the beauty of exploration. The more we find, the more we realize how much is still waiting to be discovered. Just when we thought orbital mechanics had no more surprises left, the universe threw us another curveball, the Fly-By Anomaly. Picture this: a spacecraft swings by Earth, using our planet's gravity like a slingshot to boost its speed toward some distant destination. Engineers calculate its trajectory down to the millimeter, accounting for every known force: gravity, atmospheric drag, even the faint pressure of sunlight. But then, something bizarre happens. The spacecraft doesn't behave as predicted. It either gains or loses speed ever so slightly, as if an invisible hand gave it an unexpected nudge. These discrepancies might sound trivial, mere millimeters per second, but in the precise world of astrophysics, they're as glaring as a wrong note in a symphony. Take the Rosetta mission, for example. In 2005 and 2007, the spacecraft performed Earth flybys on its way to study a comet. Each time, meticulous tracking revealed a tiny but undeniable speed boost that shouldn't have happened. The difference was minute, about 1.8 millimeters per second, but it was enough to send scientists scrambling for answers. At first, they assumed it was a glitch, maybe an error in the tracking system or an overlooked source of friction. But when Galileo, NEAR, and other spacecraft showed similar anomalies during their own flybys, the pattern became impossible to ignore. So what's really going on? One theory points to Earth's rotation. Some researchers suggest that our planet's spin might create a subtle gravitational frame dragging effect, warping spacetime in a way that nudges passing spacecraft. The math checks out mostly, but the predicted effect is far too small to explain the observed anomalies. Another idea involves Earth's atmosphere. Could residual gas molecules, even at high altitudes, interact with the spacecraft in ways we haven't fully modeled? Again, the numbers don't quite add up. Then there's the wild card, dark matter. If our planet is surrounded by a diffuse halo of this mysterious substance, could its gravitational influence be altering spacecraft trajectories? It's a tantalizing thought, but without direct evidence, it remains speculative. The most unsettling possibility, that we're seeing hints of new physics, a flaw in Einstein's general relativity that only reveals itself under very specific conditions. Modified gravity theories, like M&D, have been proposed to explain galactic rotation curves without invoking dark matter. Could the Fly-By Anomaly be another clue that gravity behaves differently on smaller scales than we thought? Or perhaps there's an undiscovered force at play, something akin to the hypothetical fifth force that pops up in fringe physics discussions. What makes the Fly-By Anomaly so fascinating isn't just the mystery, it's the stakes. These tiny speed changes might seem insignificant, but they're happening right in our cosmic backyard, where we've supposedly mastered the rules. If we can't explain them, it's like discovering your GPS works perfectly everywhere except your own neighborhood. Every unexplained millimeter is a whisper that our understanding of the universe might be missing a page or an entire chapter. And that's the real thrill of science, not the answers we have, but the anomalies that keep us questioning. Black holes aren't just cosmic vacuum cleaners, they're existential riddles wrapped in event horizons. And perhaps no puzzle is more baffling than the black hole information paradox, a clash between two pillars of physics so profound it threatens to unravel our understanding of reality itself. Here's the core of the problem. Quantum mechanics insists that information, the fundamental blueprint of every particle state, can never be destroyed. Yet Stephen Hawking showed that black holes evaporate over time, emitting faint radiation that carries away their mass. If the hole vanishes entirely, what happens to all the information it swallowed? According to Hawking's math, it's erased from existence, a direct violation of quantum law. This isn't just a technical hiccup, it's a crisis at the heart of physics, forcing scientists to ask, does information escape somehow, or is space-time far stranger than we ever imagined? The stakes couldn't be higher. If information truly vanishes, it means the universe has a built-in delete button, undermining the predictability that quantum theory relies on. Imagine burning a book and being told its pages could someday be reconstructed from the ashes. That's the promise of quantum mechanics. But black holes, it seems, burn the ashes too. For decades, physicists assumed the information was simply trapped inside, hidden behind the event horizon. Yet Hawking radiation changed everything. Those faint particles escaping the black hole's grip appear random, carrying no trace of the original matter that fell in. It's like shredding a library's worth of books into confetti and claiming the words could still be read in the scattered pieces. Enter the holographic principle, one of the most daring ideas to resolve the paradox. It suggests that all the information swallowed by a black hole isn't lost, it's encoded on its surface, painted onto the event horizon like a cosmic fresco. Think of it as a two-dimensional barcode storing the data of everything that fell inside. When the hole evaporates, this information could be released in subtle patterns within the radiation, a hidden message in the static. Recent breakthroughs like the discovery of soft hair, low-energy quantum imprints around black holes hint at how this might work, but the devil's in the details. If the information escapes, how and why does Hawking radiation look so random? Then there's the firewall hypothesis, a radical twist that's as unsettling as it sounds. If information can't be destroyed, maybe it never actually enters the black hole. Instead, the event horizon might be a seething wall of energy, incinerating anything that crosses it and converting it into a holographic record. Picture walking toward what you think is a waterfall, only to discover it's a sheet of fire, an illusion of safety hiding unimaginable violence. Critics argue this would violate Einstein's principle that crossing the horizon should feel uneventful, a smooth descent into gravity's grip. But the paradox demands bold ideas, even if they rewrite the rules. The most mind-bending possibility, that space-time itself is an emergent phenomenon, a secondary effect of deeper quantum processes. In this view, black holes aren't just objects, they're laboratories exposing the seams of reality. The information paradox might be a clue that our concepts of inside and outside a black hole are illusions, like a flatlander trying to comprehend a sphere. String theory, loop quantum gravity, and other frameworks are racing to piece together this puzzle, each offering glimpses of a universe far more interconnected than we thought. What makes this debate so electrifying isn't just the physics, it's the philosophical weight. If information can be lost, reality might be less deterministic than we assumed. If it's preserved, the universe could be storing data in ways we've yet to fathom. Every solution proposed so far comes with trade-offs, forcing us to question which laws are sacrosanct and which might be flexible. The black hole information paradox isn't just a problem to solve, it's a mirror held up to the limits of human knowledge, showing us how much we still don't understand about the fabric of existence. And in that uncertainty lies the thrill of discovery, the chance to rewrite not just textbooks, but the very definition of reality itself. Stretching across an almost unimaginable expanse of space, the Eredana Supervoid is a cosmic chasm so vast it could swallow thousands of galaxies whole, yet it's almost entirely empty. This staggering void, measuring roughly 1.8 billion light-years across, isn't just a curiosity, it's a direct challenge to our understanding of how the universe structures itself. And here's where the plot thickens. It aligns eerily with the CMB Cold Spot, that enigmatic cold patch in the cosmic microwave background we've already explored. The odds of these two anomalies overlapping by chance, astronomers put it at less than 1 in 20,000. So what's really lurking in this cosmic dead zone? The discovery of the Eredana Supervoid reads like a detective story. For years, scientists puzzled over the cold spot, testing one hypothesis after another. Then, in 2015, a team mapping galaxy distributions made a breakthrough. They found a corresponding underdensity in the same region, a void so colossal it defied conventional models of cosmic structure. Most voids are small, temporary bubbles in the cosmic web, but this one is a gaping absence, a place where matter seems to have been scooped out on an unprecedented scale. The implications are profound. If voids this large exist, it means the universe's matter distribution isn't as uniform as we thought, undermining the cosmological principle that's guided astronomy for centuries. But the real mystery is the connection to the cold spot. According to standard physics, a void this size should cool light passing through it via the integrated Sachs-Wolf effect, exactly what we see in the CMB. Yet here's the catch: the Eredana Supervoid, enormous as it is, still isn't large enough to explain the cold spot's extreme temperature drop. It's like finding a crater and realizing the meteor that made it would have had to be 10 times bigger. This mismatch has led to some radical theories. Could the void be a scar from a collision with another universe, a multiverse bruise magnified by the void's emptiness? Or is it evidence of an exotic phase transition in the early universe, a moment when space-time itself reconfigured, leaving behind a fossilized bubble of nothingness? Then there's the dark energy angle. If dark energy, the force accelerating cosmic expansion, behaves differently in these voids, it could amplify their gravitational effects, turning them into cosmic magnifying glasses for primordial anomalies. Alternatively, the void might be a rare fluctuation, a statistical outlier in an otherwise uniform cosmos, but with odds so slim, rare starts feeling like an understatement. It's as if you shuffled a deck of cards and it came out perfectly ordered twice in a row. What makes the Eredana Supervoid so captivating isn't just its size or its defiance of expectations, it's the way it forces us to rethink the universe's architecture. Are voids like this a sign of exotic physics, or simply the universe's way of reminding us how little we truly know? Every anomaly, every cosmic glitch, is a clue waiting to be deciphered. And in the case of the Eredana Supervoid, the answer might rewrite not just our maps of the cosmos, but the very rules we use to navigate them. Somewhere beyond the edge of everything we can see, something unimaginably vast seems to be pulling at entire galaxy clusters like a cosmic undertow. This is the dark flow, an eerie, unexplained motion first detected in 2008 when astronomers noticed hundreds of massive galaxy clusters drifting in the same direction at staggering speeds of nearly 2 million miles per hour. What makes this so unsettling? Their movement can't be explained by any known gravitational source within our observable universe. It's as if these galaxies are caught in a river flowing toward some colossal attractor that lies beyond the cosmic horizon, in regions of space and time forever hidden from our view. The discovery came from meticulous analysis of the cosmic microwave background. As galaxy clusters race through space, their hot gas scatters CMB photons in a telltale pattern called the kinematic Sunyaev-Zeldovich effect. When scientists mapped these distortions, they expected random motion, the gentle tug of war of local gravity. Instead, they found a coordinated march toward the constellations Centaurus and Vela, as though the universe itself had a secret current. Even accounting for all known superclusters and the Great Attractor's pull, the scale and uniformity of this motion defied explanation, the simplest conclusion. Something enormous, something outside our cosmic bubble, is exerting gravitational influence on everything we can observe. Now, here's where it gets truly mind-bending. If the dark flow is real, it implies one of two radical possibilities. First, our universe might bear scars from events that predate the Big Bang. Imagine space-time isn't a one-time creation but a mosaic, stitched together from fragments of an earlier cosmos. In this scenario, the dark flow could be the gravitational echo of a neighboring universe bubble that collided with ours in the unimaginable past, leaving behind a tidal pull frozen into the fabric of reality. Alternatively, it might hint at an eternal inflation, a multiverse where new universes constantly bud off from one another, and our patch of space-time is still subtly connected to its parent. The second possibility, that Einstein's relativity breaks down on scales larger than we've tested. Some modified gravity theories suggest that what we perceive as dark flow could be space-time itself subtly warping over cosmic distances, a curvature so gradual it's only visible when tracking motion across billions of light years. But even these exotic models struggle to explain the dark flow's precise alignment and speed without invoking influences from beyond our cosmic horizon. Critics argue it might all be a measurement error, an artifact of incomplete CMB data or uneven galaxy surveys. Yet each time astronomers reanalyze the evidence, the signal persists. The latest studies, using data from the Planck satellite and X-ray observations of thousands more clusters, continue to find the same mysterious drift. If it's not a fluke, the implications rewrite cosmology. Either our universe isn't as isolated as we thought, or the laws of physics hold secrets we've yet to uncover. What makes the dark flow so electrifying isn't just the science, it's the sheer audacity of the questions it forces us to confront. Are we living in a multiverse? Did time and space exist before the Big Bang? And if so, what else lies beyond the edges of our perception? Like sailors sensing an unseen tide, we're left to wonder. The universe may be far stranger and far more connected than we ever dared to dream. For decades, weakly interacting massive particles, WIMP, were the golden child of dark matter theories, a perfect solution hiding in plain sight. The logic was elegant. If dark matter makes up 85% of the universe's mass, it must consist of particles that don't interact with light, but still have enough heft to sculpt galaxies with their gravity. WIMP fit the bill beautifully: hypothetical particles born from supersymmetry theory, heavy enough to leave a gravitational footprint, yet elusive enough to evade detection for billions of years. The best part, according to calculations, these particles should have been forged in the fires of the Big Bang, in just the right abundance to explain the universe we see today. Physicists called it the WIMP miracle, a cosmic coincidence so perfect it seemed almost too good to be true. But the universe loves a plot twist. Despite decades of hunting with exquisitely sensitive detectors, buried deep underground where layers of rock shield against cosmic noise, WIMP have stubbornly refused to show up. Experiments like LUX Xenon and Panda X have scanned for faint recoils from WIMP bumping into atomic nuclei, listening for whispers in the dark. The result? Silence, not a single confirmed signal. It's like setting up microphones in a forest where you're certain a rare bird sings, only to hear nothing but the wind. This leaves scientists at a crossroads. Maybe WIMP are just shy, ricocheting off atoms too delicately for current tech to catch. Some theories suggest they interact even more weakly than predicted, slipping through our detectors like ghosts through walls. Others propose that WIMP aren't particles at all, but primordial black holes forged in the chaos of the early universe. Then there's the radical idea that dark matter isn't a single substance but a zoo of particles, each playing a different role in shaping the cosmos. The most tantalizing possibility, that dark matter isn't just invisible, it's alien in ways we haven't yet imagined. Theories now flirt with dark sectors, entire shadow realms of particles and forces that barely interact with ordinary matter. Picture an entire parallel universe woven through our own, its presence only betrayed by gravity. Some models even suggest dark matter could form its own dark atoms, clumping into structures we can't see. What makes this search so thrilling isn't just the mystery, it's the sheer creativity it demands. Every null result forces physicists to think bigger, to stretch the boundaries of what's possible. Whether WIMP are waiting to be found or we're on the brink of a paradigm shift, one thing's certain: the universe isn't done surprising us, and in that uncertainty lies the excitement of discovery, the chance to rewrite the rules of reality itself. Imagine looking at a streetlight through fog. The farther away it is, the dimmer it appears. That's how astronomers expected distant galaxies to behave as the universe expands. But when they put this assumption to the test using the Tolman surface brightness method, the cosmos threw them a curveball. Galaxies billions of light years away weren't just dimmer, they were too dim, as if the fog of space itself was thickening over time. This discrepancy isn't just a minor calibration error. It's a direct challenge to one of cosmology's bedrock principles, that the universe expands uniformly, with galaxies receding from each other like raisins in rising dough. The Tolman test works by comparing a galaxy's apparent brightness to its apparent size. In a static universe, these two properties should balance out. Bigger galaxies spread their light over more area, so their surface brightness stays constant regardless of distance. But in an expanding universe, light gets stretched into longer, redder wavelengths, and the energy of each photon drops. That's why we expect distant galaxies to appear fainter. The problem: they're fading faster than Einstein's relativity predicts, as if something extra is sapping their light. One explanation is as startling as it is transformative: dark energy, the mysterious force accelerating cosmic expansion, might not be constant after all. For years, scientists treated it as a fixed property of space, Einstein's cosmological constant, a steady push against gravity's pull. But if dark energy is growing stronger over time, it could explain the Tolman anomaly. Picture blowing up a balloon with air that suddenly gets hotter. The rubber stretches faster, and the dots on its surface race apart more violently. In cosmic terms, this would mean the universe's expansion isn't just accelerating, it's doing so in fits and starts, warping the light from ancient galaxies in ways we didn't anticipate. There's another, even wilder possibility, that our understanding of light itself is incomplete. Could photons lose energy over vast distances through some unknown interaction with the fabric of space? Theories like tired light, or once dismissed as fringe, are getting a second look, though they'd require rewriting much of modern physics. Others suggest the anomaly points to hidden dimensions or variations in the speed of light across cosmic history. But the most tantalizing clue lies in the timing. The Tolman effect seems to kick in around 5 billion years ago, coincidentally, the same epoch when dark energy is thought to have overtaken gravity as the universe's dominant force. What makes this discovery so revolutionary isn't just the data, it's the way it forces us to rethink the universe's very heartbeat. If dark energy evolves, it means the cosmos isn't just expanding, it's transforming with rules that change over time. Future telescopes like the Vera Rubin Observatory could settle the debate by mapping billions of galaxies with unprecedented precision. Until then, the Tolman test remains a cosmic riddle, one that might hold the key to understanding whether the universe's fate is a slow fade, a runaway explosion, or something stranger still. Our galaxy isn't flying solo through the cosmos. It's surrounded by a retinue of dwarf galaxies, tiny cosmic companions that should be scattered randomly like marbles tossed onto a floor. But here's the catch, they're not. Instead of a chaotic swarm, these satellites orbit the Milky Way in an eerily thin, pancake-like plane, a formation so precise it defies everything our simulations predict. According to the standard model of cosmology, dark matter's gravitational pull should have left these galaxies in a messy, spherical halo around us. The fact that they're arranged in a razor-thin disk isn't just unexpected. It's a direct challenge to our understanding of how dark matter shapes the universe. This puzzle, known as the satellite disk problem, first came to light when astronomers mapped the motions of the Milky Way's dwarf galaxies and realized something was off. These tiny galaxies, like the Large and Small Magellanic Clouds, aren't just orbiting haphazardly. They're moving in sync, tracing out a vast, flat structure that seems almost orchestrated. Even stranger, the same pattern appears around our galactic neighbor, Andromeda, where many of its satellites also cling to a narrow plane. The odds of this happening by chance? Less than 1 in 100. So why does reality clash so starkly with theory? One possibility is that our simulations are missing a key ingredient. Dark matter, the invisible scaffolding of the cosmos, is thought to clump into diffuse halos around galaxies, gently tugging nearby objects into random orbits. But what if dark matter interacts with itself in ways we haven't accounted for? Some theorists suggest it might have a faint stickiness, a weak force beyond gravity that lets it form flattened structures. Others propose these dwarf galaxies aren't primordial at all. They could be fragments torn from larger galaxies during ancient collisions, their orbits naturally aligning into a disk over time. Then there's the more radical idea that an unseen force is at work, something beyond dark matter. Could there be long-range fields or exotic particles subtly herding these galaxies into formation? A handful of scientists have even floated the notion of modified gravity, the idea that Einstein's equations break down on galactic scales, warping orbits in ways that mimic a disk. But these theories remain controversial, often creating more problems than they solve. The most tantalizing clue might lie in the cosmic web itself. Recent simulations suggest that the vast filaments of dark matter threading the universe could funnel dwarf galaxies into aligned paths as they fall toward larger galaxies like the Milky Way. Picture water droplets sliding down a spider's web. Their paths aren't random but guided by the web's structure. If true, it would mean the satellite disk problem isn't a flaw in our models but a sign of something deeper, the hidden architecture of the cosmos, written in the motions of its smallest galaxies. What makes this mystery so compelling isn't just the science, it's what it reveals about our place in the universe. We're not just passive observers of the cosmos, we're detectives, piecing together clues from the faintest whispers of light. Every anomaly, every unexpected alignment, is a chance to peek behind the curtain of reality. And in the case of the satellite disk problem, the answer might not just rewrite our understanding of dark matter, it could redefine how galaxies dance through the void. They slip through planets like ghosts through walls, billions passing through your body every second without a trace. Neutrinos, the universe's most elusive particles, were long thought to be massless, zipping through space at the speed of light without a care for gravity or matter. But in the late 90s, a bombshell discovery shattered that assumption. Scientists found these spectral particles oscillating, changing flavors between electron, muon, and tau neutrinos as they traveled, a phenomenon that's only possible if they have mass. The revelation was like learning a shadow could gain weight. It didn't just upend particle physics, it punched a hole right through the standard model, the meticulously crafted rulebook that had governed our understanding of the subatomic world for decades. So how much mass are we talking about? Here's the twist: neutrinos are absurdly lightweight. The heftiest neutrino is at least 10 million times lighter than an electron, itself a featherweight next to protons. But in physics, even the tiniest discrepancy can ripple into a revolution. The standard model had no slot for massive neutrinos. Their existence implies entirely new physics, particles or forces we've yet to discover. One tantalizing possibility, that neutrinos are their own antiparticles, a hypothetical trait called Majorana mass. If true, it could explain why the universe is made of matter rather than antimatter. Picture a cosmic scale tipping in favor of existence itself, all because of these nearly weightless particles. Then there's the dark matter connection. Some theories suggest sterile neutrinos, a hypothetical fourth flavor that doesn't interact with anything except gravity, could be the invisible scaffolding of the cosmos. These shadowy particles would weave through galaxies, shaping them with their gravity while remaining forever undetectable by conventional means. Experiments like Mini, Bueni, and Ice Cube are hunting for hints of these phantoms, but so far, the evidence is as elusive as the particles themselves. But the wildest speculation ties neutrinos to extra dimensions. In string theory, our universe might be a four-dimensional membrane floating in a higher dimensional space. Neutrinos, with barely their mass, could be the only particles sensitive to these hidden dimensions, their slight weight a fingerprint of gravity leaking from other realms. It's a dizzying thought that the answer to the neutrino mass puzzle might not just rewrite particle physics, but redraw the very map of reality. What makes this anomaly so thrilling isn't just the science, it's the humility it demands. The standard model has been physics' crowning achievement for half a century, predicting everything from the Higgs boson to quantum quirks with uncanny precision. Yet here we are, staring at a handful of nearly massless particles that refuse to fit the mold. They're a whisper from the universe, reminding us that even our most brilliant theories are just sketches of a deeper, stranger truth. And in that mystery lies the joy of discovery, not just finding answers, but learning how much more there is to ask. Science is often portrayed as a march of steady progress, but the history of the Hubble-Lemaître Law, the discovery that the universe is expanding, reads more like a cosmic detective story with contested clues, rival investigators, and a lingering mystery that still haunts cosmology today. The tale begins in the 1920s, when Edwin Hubble and Georges Lemaitre independently studied the light from distant galaxies and noticed something peculiar. The spectral lines of these galaxies were shifted toward the red end of the spectrum, a sign that they were racing away from us. More astonishingly, the farther away a galaxy was, the faster it seemed to be receding. This wasn't just random motion, it was evidence that space itself was stretching, carrying galaxies along with it like raisins in an inflating loaf of bread. But behind this landmark discovery lies a simmering controversy. While Hubble's name became synonymous with the expanding universe, thanks in part to the telescope later named in his honor, Lemaitre had actually published similar findings 2 years earlier. His 1927 paper, written in French and buried in an obscure journal, derived the same mathematical relationship between distance and velocity, even proposing what we now call the Hubble constant. Yet when Hubble's work appeared in 1929, Lemaitre's contribution was largely overlooked, a casualty of language barriers and the scientific spotlight favoring established institutions. It wasn't until 2018 that the International Astronomical Union officially renamed the law to include Lemaitre, correcting a historical oversight. But the debate over credit is just the surface of a much deeper puzzle. The real intrigue lies in the data itself. Hubble's original measurements were groundbreaking, but they were also riddled with errors. His estimates of galactic distances relied on Cepheid variable stars' cosmic yardsticks, whose brightness pulses at a rate tied to their true luminosity. By comparing this intrinsic brightness to how dim they appeared from Earth, Hubble calculated their distances, but his calculations were off by nearly 7-fold, a mistake that skewed his expansion rate. Later astronomers, using better tools and techniques, refined the numbers, yet discrepancies persisted. Even today, as we grapple with the Hubble tension, the clash between early and late universe expansion rates, we're forced to ask, were these early missteps merely technical hiccups, or could they hint at something more profound? One tantalizing possibility is that the expansion rate isn't just a number, it's a Rosetta Stone for decoding the universe's hidden architecture. If the Hubble constant varies depending on how or where we measure it, it might suggest that dark energy isn't uniform but evolves over time. Imagine blowing up a balloon with patches of thinner rubber. Some areas would stretch faster than others. Similarly, if dark energy's repulsive force is stronger in certain cosmic epochs or regions, it could explain why different measurement methods yield conflicting results. Alternatively, the early universe might have hosted exotic particles or fields that temporarily altered the expansion rate, leaving behind a ghostly imprint in today's measurements. Then there's the radical notion that our corner of the cosmos is atypical, a vast underdense region where gravity's grip is weaker, making local expansion appear faster. Think of it like standing in a valley and assuming the whole world slopes downward. If we're inside a Hubble bubble, our measurements could be skewed by our limited perspective. This idea gains traction from the KBC Void we discussed earlier, but it's still far from settled science. What makes this controversy so riveting isn't just the historical drama or the technical nuances, it's the humility it demands. The Hubble-Lemaître Law isn't just a triumph of human curiosity. It's a reminder that even our most foundational discoveries are works in progress. Every time we refine the expansion rate, every time we debate its implications, we're not just correcting the past, we're inching closer to truths that might rewrite the future of cosmology. And in that tension between what we know and what we've yet to uncover lies the heartbeat of scientific discovery. At the smallest scales imaginable, where the fabric of reality frays into a frenzy of uncertainty, space-time itself might not be the smooth, unbroken continuum we once imagined. Instead, it could be a seething ocean of turbulence, a quantum foam where space and time twist, writhe, and flicker in and out of existence. This isn't poetic exaggeration. It's a radical prediction born from the collision of two titanic theories, quantum mechanics and general relativity. According to this idea, if you could zoom in on spacetime until you reached scales a billion trillion times smaller than an atom, you'd find a frothing chaos of virtual particles, wormholes, and microscopic black holes popping in and out of existence like bubbles in a boiling pot. The concept of quantum foam isn't just a wild thought experiment, it's a mathematical necessity. Quantum mechanics tells us that empty space is never truly empty. Even in a perfect vacuum, particles and antiparticles constantly emerge in pairs, borrowing energy from the universe before annihilating each other in a flash of borrowed time. This quantum fluctuation means spacetime itself is subject to the same rules, churning with energy at scales so tiny we've never directly observed them. But here's where things get even stranger. These fluctuations could be the key to one of cosmology's biggest mysteries, dark energy. Imagine the quantum foam as an invisible, bubbling undercurrent beneath reality. Every fluctuation, every microscopic wormhole or black hole that flickers into being, carries a tiny amount of energy. Add up all these fluctuations across the entire universe, and you're left with an astonishing possibility. This foam might be the source of the repulsive force we call dark energy, the very thing driving the universe's accelerated expansion. It's a tantalizing idea that the largest scale phenomenon in the cosmos could be fueled by the smallest, most frenzied activity imaginable, but not everyone's convinced. Critics argue that quantum foam might be a mathematical mirage, an artifact of theories pushed beyond their limits. When we try to marry quantum mechanics with general relativity, the equations often spit out infinities, nonsensical results that suggest our models are incomplete. Some physicists propose that quantum foam is just a placeholder, a signpost pointing toward a deeper theory we haven't yet discovered, like string theory or loop quantum gravity. Others wonder if we're missing something fundamental, a hidden variable or symmetry that would smooth out the foam into something more orderly. The debate gets even thornier when we consider how to test this idea. Quantum foam operates at scales far beyond the reach of our most powerful particle colliders, but astronomers have devised clever workarounds. Some look for subtle distortions in the light from distant gamma-ray bursts. If spacetime is foamy, high-energy photons should arrive slightly out of sync with lower-energy ones, their paths jostled by the microscopic turbulence. Others search for telltale noise in gravitational wave detectors, hoping to catch the faint whispers of spacetime itself shuddering at the smallest scales. So far, the evidence is inconclusive, but the hunt is far from over. What makes quantum foam so electrifying isn't just the science, it's the philosophical weight. If spacetime is fundamentally frothy, it means our smooth, continuous universe is an illusion, a statistical average of unimaginable chaos beneath. It's like realizing the calm surface of a lake hides a storm of molecular motion just beneath. And if this foam truly fuels dark energy, it would mean the fate of the cosmos, whether it ends in a cold, empty fade or a violent rip, is written in the behavior of particles we can't even see. That's the real magic of quantum foam. It's not just a curiosity for theorists, it's a bridge between the infinitesimally small and the cosmically vast, a reminder that the universe's deepest secrets might be hidden in plain sight if only we know where to look. And as we peer deeper into the foam, we're not just studying spacetime, we're unraveling the very fabric of reality itself. Quasars should be cosmic lighthouses, steady, predictable beacons whose light tells a clear story of their distance and motion. But some of these brilliant objects refuse to follow the script, displaying redshift so extreme they defy conventional physics. Redshift, the stretching of light toward longer wavelengths as objects move away from us, is the bedrock of cosmic distance measurement. The greater the redshift, the faster an object is receding, and the farther away it should be. Yet certain quasars break this rule with redshifts that place them at impossible distances, racing away faster than the universe itself should allow. Either our measurements are fundamentally flawed, or these objects are revealing a cosmic mystery that could rewrite the way we map the heavens. Take the case of Quasar 3C191, one of the first to shatter expectations. Its redshift suggested it was hurtling away at nearly 90% the speed of light, implying a distance so vast its light should have taken over 10 billion years to reach us. But here's the catch: the galaxy seemingly hosting this quasar had a much lower redshift, indicating it was far closer. How could two objects apparently bound by gravity have such wildly different velocities? Skeptics argued the pairing was an illusion, a chance alignment of a distant quasar with a foreground galaxy. Yet as more of these mismatched systems were discovered, coincidence became harder to swallow. One radical explanation: quantized redshift, the idea that redshifts aren't smooth and continuous but instead cluster at specific intervals, like rungs on a cosmic ladder. If true, it would mean the universe has a hidden structure with matter arranged in concentric shells around us. Proponents of this view, like astronomer Halton Arp, pointed to peculiar galaxies with multiple quasars nearby, all sporting different redshifts despite appearing physically connected. Arp's controversial conclusion: redshift isn't purely a measure of distance but also carries imprints of an object's intrinsic properties, perhaps tied to its age or composition. Mainstream cosmology dismissed this as statistical noise, but the anomalies persisted, whispering of unseen forces at play. Then there's the Doppler dilemma. Traditional redshift assumes objects move uniformly, like cars on a highway. But what if some quasars are cosmic slingshots, ejected from galaxies at blistering speeds by supermassive black holes? Simulations show black hole binaries can fling stars away at relativistic velocities. Could the same happen to quasars? Others suggest the redshift anomalies might stem from light passing through regions of warped spacetime, where dark matter or exotic energy stretches photons like taffy. The most unsettling possibility: that the universe's expansion isn't as uniform as we thought, with pockets of space accelerating faster than others, skewing our cosmic yardsticks. The stakes couldn't be higher. If redshift is an unreliable guide, the cosmic distances we've painstakingly mapped, the very framework of modern cosmology, might need recalibration. Imagine building a house only to discover your tape measure was faulty all along. Future telescopes, like the James Webb, could settle the debate by scrutinizing these rogue quasars in unprecedented detail. Until then, the redshift controversy remains a tantalizing loose thread in the fabric of cosmology, pulling us toward a truth that might be stranger than fiction. After all, the universe has never been one to follow rules. Why start now? Deep beneath the rugged peaks of Italy's Gran Sasso Mountain, shielded from cosmic interference by 1,400 meters of solid rock, an experiment has been quietly recording a signal that could rewrite the dark matter story or expose one of physics' most stubborn red herrings. For over 2 decades, the Dama/Libra collaboration has reported an annual flicker in their detector's data, a rhythmic pulse that peaks every June and fades by December. Their bold claim: these fluctuations are the fingerprints of dark matter particles streaming through Earth as we orbit through our galaxy's shadowy halo. Here's why this seasonal signal is so compelling. If the Milky Way is indeed embedded in a vast cloud of dark matter, our solar system should be plowing through this invisible wind as it circles the galactic center. Earth's orbit would add or subtract speed relative to this wind depending on the time of year, like a cyclist pedaling with or against a breeze. In June, when our planet moves in the same direction as the solar system's galactic motion, we'd theoretically encounter more dark matter particles. By December, when our motion opposes the flow, the apparent wind should slacken. Dama sodium iodide crystals, designed to light up when particles collide with their atomic nuclei, seem to capture exactly this ebb and flow, a tantalizing synchronization with cosmic mechanics. Yet the scientific community remains sharply divided. Not a single other experiment, from the ultra-sensitive xenon detectors buried in South Dakota's Black Hills to the cryogenic germanium arrays in Spain's Canfranc Tunnel, has replicated Dama results. Critics point to mundane explanations, trace radioactivity in the detector's components, subtle temperature variations in the underground lab, or even the seasonal rise and fall of groundwater altering the local radiation environment. The Dama team, however, stands firm. They've systematically ruled out these possibilities across multiple detector upgrades, watching the signal persist with unwavering statistical significance. The plot thickens when you consider what kind of dark matter could produce such a signal. Most theories favor WIMP, weakly interacting massive particles, but Dama data suggests something lighter and more nimble, perhaps as light as a proton. This hypothetical particle, dubbed the dark photon, would interact just enough to nudge atomic nuclei without leaving the more dramatic trails heavier WIMP should create. Intriguingly, this could explain why other experiments haven't spotted it. Their detectors might literally be tuned to the wrong frequency, like radios missing a faint station between static. What makes this mystery so gripping isn't just the scientific stalemate, it's the human drama underneath. Dama researchers have endured decades of skepticism, refining their methods while rivals build ever more sensitive experiments designed specifically to disprove them. The tension mirrors the early days of neutrino physics, when theory outpaced detection for generations. Could history be repeating itself, with Dama as the modern equivalent of those first stubborn neutrino hunters? Or is this a cautionary tale of confirmation bias, where a team has fallen in love with a signal that isn't there? As new experiments like Cosine 100 and SABRE deploy identical sodium iodide crystals to test Dama claims, the answer may finally be within reach. Whatever the outcome, this decades-long saga captures the essence of scientific progress, not as a straight path to truth, but as a winding road where every anomaly, every disagreement, forces us to sharpen our questions and refine our tools. The universe's secrets rarely surrender easily, and Dama enduring enigma reminds us that the most tantalizing discoveries often lie just beyond the edge of what we can prove. Among the sea of darkness between galaxies, there's a faint, omnipotent glow, one that shouldn't exist. This is the cosmic infrared background, a diffuse light bathing the universe in wavelengths invisible to our eyes but blazingly obvious to our telescopes. Unlike the cosmic microwave background, which tells the story of the universe's fiery infancy, this infrared hum speaks of something far more elusive: the hidden lives of the first stars, galaxies, or perhaps even processes we haven't yet imagined. The puzzle isn't just that the light exists, it's that there's too much of it, as if the cosmos left the lights on in rooms we didn't know existed. When NASA's Spitzer Space Telescope first mapped this background in detail, astronomers expected a predictable fade as they looked deeper into the past. Instead, they found patches of infrared light far brighter than any known population of early galaxies could produce. It's like walking into a forest at night and hearing a chorus of crickets only to realize the sound is coming from empty trees. The leading theory: this glow might be the collective radiance of the universe's very first stars, monsters known as population Roman 3 stars. These hypothetical giants, hundreds of times more massive than our Sun, would have burned ferociously bright and died young, leaving behind no trace but their infrared afterglow. But here's the twist. Even if every one of these primordial stars blazed at maximum efficiency, their combined light still falls short of explaining the observed signal. That discrepancy has sent scientists scrambling for alternatives. Could supermassive black holes in the early universe, voraciously devouring gas, have pumped out excess infrared as they fed? Or might decaying particles from the dark matter sector, exotic relics of the Big Bang, be slowly releasing energy as they vanish? Some theorists even speculate about dark stars, hypothetical objects powered not by nuclear fusion but by the annihilation of dark matter particles in their cores. The implications are staggering. If the infrared background stems from unknown astrophysical processes, it could mean galaxies formed earlier and faster than our models predict, compressing cosmic history into a tighter timeline. Alternatively, if the glow hints at new physics like interacting dark matter, it might be the first tangible clue to a shadow universe woven into our own. The James Webb Space Telescope is now hunting for answers, peering back to the era where this mysterious light originated. Every flicker it captures could rewrite not just the story of galaxy formation, but the very nature of the invisible forces shaping the cosmos. What makes this enigma so captivating isn't just the science, it's the way it forces us to confront the limits of our cosmic vision. The universe isn't just hiding its secrets in black holes or distant galaxies, it's whispering them in wavelengths we're only beginning to decode. And in that whisper lies a reminder: the more we see, the more we realize how much we've yet to discover. Rising like colossal hourglasses from the heart of our galaxy, the Fermi Bubbles stretch 50,000 light-years above and below the Milky Way's disk, twin towers of gamma-ray energy so vast they dwarf our entire solar system. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these gargantuan structures glow with the fury of a million suns, yet their origin remains one of the most heated debates in modern astrophysics. What cosmic event could have punched such enormous cavities through interstellar space, leaving behind this lingering high-energy echo? One leading theory points to Sagittarius A, the supermassive black hole at our galaxy's center. Every few million years, these gravitational monsters awaken from their slumber, devouring nearby gas and stars in violent feeding frenzies. During one such eruption, roughly 2.5 million years ago, SGR might have blasted jets of plasma straight up and down the galactic poles, inflating these bubbles like cosmic balloons. Supporting this idea are the bubbles' sharp edges, evidence of a rapid, explosive event rather than slow stellar winds. But here's the catch: the energy required exceeds any known black hole outburst by orders of magnitude. Even accounting for SGRA's appetite, the Fermi Bubbles gamma-ray output defies conventional models, as if the black hole temporarily became a cosmic blowtorch of unimaginable power. Then there's the dark matter angle. Some theorists propose these bubbles are the aftermath of a catastrophic particle collision, ancient clouds of dark matter annihilating near the galactic core, releasing bursts of gamma rays as they vanished. If true, it would be the first tangible evidence of dark matter's hidden interactions, a smoking gun in one of physics' greatest mysteries. Yet skeptics counter that the bubble's symmetrical structure and smooth emission spectrum don't quite match predictions for dark matter annihilation. The plot thickens when you consider the bubble's microwave haze, a counterpart glow seen by the Planck satellite energy signatures that might trace shock waves from the same cataclysm. Perhaps most intriguing is the timing coincidence. The bubble's estimated age aligns suspiciously well with another cosmic anomaly, the Pliocene marine megafauna extinction, a mysterious die-off of large sea creatures around the same epoch. Could a burst of radiation from the galactic center have subtly altered Earth's atmosphere or magnetic field? It's a speculative leap, but the universe has surprised us before. What makes the Fermi Bubbles so mesmerizing isn't just their scale, it's what they reveal about our galaxy's hidden violence. We think of the Milky Way as a relatively quiet suburb in the cosmic metropolis, but these structures paint a different picture, one of intermittent fury, where even dormant black holes can reshape their surroundings in moments of apocalyptic energy. Future telescopes, like the Cherenkov Telescope Array, may finally decode their origins by mapping the bubble's finer structure. Until then, they stand as silent monuments to the forces that shape galaxies, and perhaps in ways we don't yet understand, the very conditions that make life possible. In the vast, silent expanse of space, invisible bullets are constantly raining down on Earth cosmic rays, carrying energies so unfathomably high they defy the known laws of physics. The most extreme of these, dubbed the O.M.G particle, struck our atmosphere in 1991 with the kinetic energy of a well-thrown baseball compressed into a single subatomic particle. To put that in perspective, this one tiny particle hit with 50 joules of energy millions of times more powerful than anything our most advanced particle colliders can produce. It was moving at 99.999999999% the speed of light, carrying energy levels that simply shouldn't exist under our current understanding of astrophysics. Here's the puzzle: space shouldn't be able to make particles this energetic. Cosmic rays typically gain speed by surfing on shockwaves from supernovas or getting whipped around by black holes, but even those extreme environments have theoretical limits. The O.M.G particle's energy was so far beyond those limits that it's like discovering a single raindrop with the force of a tidal wave. Where could such a particle possibly come from? One idea points to active galactic nuclei, supercharged cores of distant galaxies where supermassive black holes launch jets of plasma at near light speed. These cosmic particle accelerators might, under perfect conditions, boost protons to such insane energies. But there's a catch: the farther these particles travel, the more they should lose energy by colliding with photons from the cosmic microwave background. The O.M.G particle arrived with so much energy left over that, statistically, its source would have to be within our local galactic neighborhood, yet we found nothing nearby capable of producing it. Then there's the even wilder possibility that these particles aren't coming from astrophysical sources at all. Some theorists speculate they could be evidence of exotic physics, decaying super-heavy dark matter particles, defects in space-time left over from the Big Bang, or even cosmic strings, hypothetical one-dimensional wrinkles in the fabric of reality. Imagine the universe as a tablecloth and cosmic strings as snagged threads. If one snapped, it could release enough energy to fling particles across the cosmos with unimaginable force. The real problem isn't just explaining one O.M.G particle, it's that they keep coming. Detectors like the Pierre Auger Observatory in Argentina have recorded dozens of these ultra-high-energy cosmic rays, each one a screaming contradiction of our models. They don't arrive in predictable patterns or from obvious directions, scattering across the sky like shotgun blasts from an unseen assailant. Some seem to cluster in ways that hint at hidden cosmic accelerators, while others appear completely random, as if the universe itself is playing dice with particle physics. What makes this mystery so thrilling isn't just the science, it's the sheer audacity of the challenge. These particles are nature's way of telling us our rulebook is incomplete. Every time one streaks through our atmosphere, it's a reminder that somewhere out there, in the darkness between galaxies, forces are at work that we've yet to even imagine. And until we solve their riddle, they'll keep arriving tiny messengers from the cosmos, carrying energies that defy explanation. The universe might look smooth and continuous to our eyes, but what if reality itself is built from tiny, indivisible pixels like a cosmic photograph blown up until you see the grains? This radical idea lies at the heart of quantum gravity theories, which propose that spacetime isn't an endless, flowing fabric, but a finely woven mesh with a fundamental resolution. Imagine zooming in on a digital image until the colors fracture into individual squares, except instead of pixels, you'd find Planck-length grains, the smallest possible units of space and time. At a scale 100 trillion times smaller than an atom, the smooth curves of Einstein's relativity would dissolve into a froth of discrete, jittering fragments. Why does this matter? Because it could be the key to solving physics' greatest unsolved riddle, uniting general relativity, which governs the cosmos' grand architecture, with quantum mechanics, the rulebook for the subatomic world. These two frameworks clash spectacularly at extreme scales, like inside black holes or during the Big Bang, where gravity's pull meets quantum unpredictability. Quantum gravity theories like loop quantum gravity or string theory attempt to bridge this divide by rewriting spacetime itself as something granular. In this view, the universe isn't just described by quantum laws, it is quantum, pixel by pixel. But here's the catch: these spacetime pixels are unimaginably small. The Planck length, about 10 to the minus 35 meters, is so tiny that probing it directly would require a particle accelerator the size of the Milky Way. So how do we test such an extraordinary claim? Astronomers have turned to cosmic detectives, gamma-ray bursts, the universe's most energetic explosions. When these bursts travel billions of light years to reach us, their highest energy photons should interact with spacetime's hypothetical graininess, slowing down ever so slightly compared to lower energy light. It's like rolling marbles over sandpaper. The finer the grit, the less they're slowed. Initial observations from telescopes like the Fermi Gamma Ray Space Telescope have tantalized hints. Some high-energy photons arrive a fraction of a second later than expected, as if they'd stumbled over spacetime's coarse texture. But the evidence remains murky, with competing explanations like interstellar turbulence muddying the waters. Even more provocative are experiments with quantum entangled particles. If spacetime is pixelated, entanglement, where particles remain mysteriously linked across distances, might feel that granularity, altering how correlations decay over space. Early lab results are inconclusive but electrifying, suggesting we might be on the verge of glimpsing reality's underlying code. The implications are staggering. If spacetime is pixelated, it could explain why black holes don't crush matter into infinitely dense points, but instead hit a smallest possible volume. It might reveal how the universe sprang from nothingness, not as a singularity, but as a quantum jump in the spacetime network. Some theories even suggest that cosmic pixels could store information, turning the universe into a cosmic quantum computer where every interaction is a calculation. Yet skepticism remains. Critics argue that pixelation is just one of many paths to quantum gravity, and until we see definitive proof, it's a captivating hypothesis, not a fact. Others warn that our obsession with pixels might be a human bias, projecting our digital worldview onto nature's deeper logic. After all, the true texture of reality could be something far stranger, beyond metaphors of grids or networks. What makes this quest so thrilling isn't just the science, it's the philosophical vertigo. We're peering beyond the curtain of perception, asking whether the universe is fundamentally smooth or stitched together from invisible threads. Every photon, every entangled particle, might carry clues written in a language we're only beginning to decode. And if the Planckian universe is real, it won't just rewrite physics, it'll redefine what we mean by reality itself. Imagine staring into the abyss, not a metaphor, but an actual, light-devouring void so dense it warps the very fabric of reality around it. That's exactly what the Event Horizon Telescope gave us in 2019, when it revealed the first ever image of a black hole's shadow at the heart of galaxy M87. The glowing ring of superheated gas circling the darkness matched Einstein's predictions with uncanny precision, a triumph of human ingenuity and theoretical physics. But buried in those radio waves was a whisper of something off. The shadow's shape wasn't a perfect circle, and the ring's brightness flickered asymmetrically, tiny discrepancies that could either be cosmic static or the first hints of physics beyond Einstein's masterpiece. Let's break down why this matters. A black hole's shadow isn't the event horizon itself, but the silhouette cast by light bending so severely around the hole that it creates a photon ring, a fiery halo marking the point of no return. General relativity predicts this shadow should be nearly circular, since space-time distortion smooths out irregularities. Yet M87's shadow showed subtle flattening on one side, like a slightly deflated basketball. One explanation: the black hole is spinning at breakneck speeds, dragging space-time around it like a whirlpool and twisting the shadow into a lopsided shape. But here's the catch: the spin required to produce this distortion pushes the limits of what relativity allows. Then there's the brightness asymmetry. The southern part of the ring shone noticeably brighter than the northern. This could stem from Doppler beaming, where material swirling toward us at near light speed appears brighter due to relativistic effects. But simulations suggest the asymmetry might be too extreme for even this explanation. Some theorists speculate it could reveal unexpected magnetic fields near the event horizon, structures so intense they warp plasma in ways our models don't account for. Others wonder if we're seeing evidence of quantum effects, tiny fluctuations in spacetime itself, like the quantum foam we explored earlier manifesting at macroscopic scales. The most tantalizing possibility: that these anomalies are fingerprints of a deeper theory waiting to be discovered. Einstein's equations have passed every test for a century, but black holes are where relativity famously clashes with quantum mechanics. What if the slight deviations in M87's shadow are the first observational cracks in our understanding, signs that gravity behaves differently in these extreme environments? Modified gravity theories like scalar tensor formulations or emergent gravity predict subtle changes to black hole shadows that might align with the EHT's data. Even string theory gets in on the action, with some models suggesting extra dimensions could subtly alter how black holes bend light. Of course, there are mundane explanations too. The disk of gas around M87's black hole might be turbulent, its uneven heating creating brightness variations, or our viewing angle could be slightly off, skewing the shadow's appearance. Future observations with sharper resolution, like next-generation EHT arrays or space-based radio telescopes, will help separate signal from noise. But if the anomalies persist, they could revolutionize physics as profoundly as Mercury's orbit did in Einstein's day. Back then, the tiny wobble in Mercury's path revealed the flaws in Newtonian gravity and ushered in relativity. Today, M87's imperfect shadow might be our Mercury moment, a cosmic clue that the universe still has secrets to spill. The beauty of this mystery lies in its duality. The EHT's image was both a confirmation of Einstein's genius and a quiet challenge to it, a reminder that even our most brilliant theories are approximations of a deeper truth. Every deviation, every asymmetry in that glowing ring is an invitation to look closer, to think bigger, and to wonder what other surprises these cosmic monsters might be hiding just beyond the edge of sight. Neutron stars should be the ultimate cosmic conformists, collapsed stellar cores so dense that quantum forces, not chemistry, dictate their structure. According to decades of astrophysical models, these ultra-dense remnants of supernova explosions ought to fall within a tight size range, typically between 1 and 2.2 times the mass of our Sun. But the universe, as always, loves to defy expectations. Recent observations have uncovered neutron stars that refuse to fit the mold, some so monstrously heavy they verge on collapsing into black holes, others so lightweight they shouldn't exist at all. These misfits don't just challenge our understanding of stellar evolution, they threaten to unravel the very equations that describe matter under the most extreme conditions imaginable. Take the case of J0740 plus 6620, a pulsar tipping the scales at a staggering 2.1 solar masses. At this weight, the star's core is under such unimaginable pressure that protons and electrons fuse into a sea of neutrons so tightly packed they begin to overlap. Current physics suggests this neutron soup should eventually buckle, collapsing into a black hole somewhere around 2.2 solar masses. Yet J0740 plus 6620 dances dangerously close to that edge without crossing over, as if some unseen force is propping it up. One radical solution: the neutrons themselves might be breaking down into their constituent quarks, transforming the star's core into a bizarre new state of matter. These hypothetical quark stars would resemble gigantic atomic nuclei, their particles freed from their usual partnerships to form a dense, frictionless fluid. If real, they could explain how these overweight neutron stars resist gravitational collapse, but quark matter remains purely theoretical, with no definitive proof it exists in nature. On the opposite end of the spectrum, stars like Hess J 1731-347 defy expectations by being inexplicably small. This neutron star, located 12,000 light-years away, weighs just 0.77 solar masses lighter than some white dwarfs, which are far less dense. According to conventional models, a neutron star this petite shouldn't form in the first place. Supernovas typically leave behind heavier remnants. One possibility is that it's not a neutron star at all, but a strange hybrid with a core of dark matter. Some theories suggest dark matter particles, if they interact weakly with normal matter, could accumulate inside collapsing stars, displacing neutrons and reducing the star's overall mass. It's a cosmic bait and switch. What looks like a neutron star might instead be a celestial Russian nesting doll, its true nature hidden beneath layers of ordinary matter. These anomalies aren't just academic curiosities, they're stress tests for the very laws of physics. Neutron stars are nature's ultimate laboratories, environments where densities exceed those of atomic nuclei and magnetic fields are strong enough to distort atoms. If our models can't account for their diversity, it might mean we're missing a fundamental piece of the quantum puzzle. Some physicists speculate that extreme conditions inside these stars could give rise to hyperons, exotic particles heavier than neutrons that briefly appear in particle colliders. Others wonder if neutron stars harbor undiscovered phases of matter, like superconducting quark-gluon plasmas or crystalline neutron exteriors that behave like cosmic metals. The most tantalizing clue might come from gravitational waves. When neutron stars collide, as they did in the historic 2017 event GW 170,817, they ripple spacetime in ways that reveal their internal structure. Future observatories like the Einstein telescope could detect subtle differences in these waves that betray the presence of quark matter or dark matter cores. Until then, these stellar misfits remain cosmic riddles, reminding us that even the most extreme objects in the universe still have secrets to surrender. And in those secrets might lie answers to some of physics' deepest questions about the nature of matter, the limits of gravity, and the strange, beautiful unpredictability of the cosmos. Black holes have long been the dark darlings of astrophysics' cosmic vacuum cleaners that devour everything in their path. But what if their opposites exist? Enter white holes, the theoretical yin to a black hole's yang. While black holes trap matter and light behind an event horizon from which nothing escapes, white holes would do the exact opposite, violently spewing out energy and matter while forbidding anything from entering. They're like cosmic fountains, gushing material into the universe with relentless force. And here's where the idea gets truly mind-bending. What if the Big Bang itself wasn't a singularity, but a white hole's cataclysmic outburst? This isn't just wild speculation. The math of general relativity actually permits white holes as valid solutions to Einstein's equations, just as it predicts black holes. In fact, some interpretations suggest that a white hole could be the time-reversed version of a black hole. Imagine a black hole's life played in rewind. Instead of collapsing inward forever, it would explode outward in a dazzling display of energy. Now stretch that idea to cosmic proportions. If a black hole represents the ultimate end point of gravitational collapse, a white hole could represent the ultimate beginning, a rupture in space-time where matter and energy flood into existence rather than vanish. The implications are staggering. For decades, the Big Bang has been framed as a singularity, a point of infinite density where the laws of physics break down. But singularities are mathematical headaches, places where our equations fail and predictability vanishes. White holes offer an elegant alternative. Instead of a defying logic spewing out a universe in a single, unfathomable instant, a white hole's eruption could provide a more structured birth for the cosmos. Matter wouldn't emerge from nowhere. It would be the result of a physical process, one that might even leave behind traces in the fabric of spacetime itself. Some theorists take this even further. If white holes are real, could they be connected to black holes through wormholes, Einstein-Rosen bridges that tunnel through spacetime? In this scenario, matter falling into a black hole in one region of the universe might be ejected from a white hole elsewhere, like water flowing through a cosmic pipe. It's a tantalizing thought. The Big Bang might not have been a one-time event, but the visible end of a chain reaction spanning multiple universes. Of course, there's a catch. White holes, if they exist, would be spectacularly unstable. Unlike black holes, which are thought to persist for eons, a white hole's explosive nature suggests it would quickly dissipate, making them extraordinarily rare if they form at all. Then there's the observational challenge. How do you detect something that, by definition, can't be entered or approached? Some researchers propose looking for anomalous gamma-ray bursts or high-energy particle streams that don't fit known astrophysical patterns. Others suggest the cosmic microwave background itself might bear scars from a white hole's primordial outburst, subtle asymmetries in the afterglow of creation. What makes the white hole hypothesis so compelling isn't just its audacity, it's the way it reframes our cosmic origin story. If the Big Bang was a white hole, the universe didn't emerge from a mathematical paradox. It was born from a mechanism, a physical event that might one day find its place in a larger theory of quantum gravity. And that's the true power of this idea, not just to answer old questions, but to inspire new ones. After all, if white holes are possible, what other cosmic surprises might be lurking in the equations we've yet to explore? What if the universe isn't the ultimate reality, but an elaborate simulation running on some unfathomable computer? It sounds like the plot of a sci-fi movie, but a growing number of physicists are seriously considering this possibility, not as fantasy, but as a legitimate hypothesis that could explain some of the strangest quirks in quantum mechanics. The simulation argument, first popularized by philosopher Nick Bostrom, suggests that if advanced civilizations could one day run ancestor simulations, hyper-detailed recreations of their own history, then the odds are staggeringly high that we're already inside one. And while it may seem outlandish at first glance, this idea isn't just philosophical musing. It's rooted in tangible anomalies, tiny cracks in reality that some scientists argue could be the pixelation of a simulated cosmos. Take quantum superposition, for example. Before we measure them, particles exist in multiple states at once, as if the universe hasn't decided what they should be until we look. This isn't just theoretical, it's been proven in labs with photons, electrons, even molecules. But in a simulation, this makes eerie sense. To save processing power, a computer might only render the details of a system when it's being observed, like a video game loading textures only when a player looks at them. The infamous double-slit experiment takes this further. When particles are fired at a barrier with two slits, they behave as waves unless we watch, at which point they choose a path. It's as if the simulation is cutting corners until forced to compute the outcome. Then there's the unsettling precision of the universe's constants. The speed of light, the strength of gravity, the charge of an electron. These values seem fine-tuned to allow for stars, planets, and life itself. Tweak any one slightly, and the cosmos would collapse into chaos. In a simulation, this could simply be the result of deliberate parameter settings, like a programmer dialing in the perfect conditions for their virtual world. Even the mathematical nature of reality, the fact that everything from galaxy clusters to subatomic particles obeys elegant equations, fits a digital framework. After all, what are simulations but mathematical models brought to life? But here's where skeptics push back. If we're in a simulation, where are the glitches? Some researchers point to high-energy cosmic rays, which occasionally break the supposed energy limit of the universe as potential system errors. Others cite quantum entanglement, the instantaneous connection between particles across vast distances, as evidence of a programmed shortcut, bypassing the speed of light for efficiency. Yet critics argue these phenomena have natural explanations within standard physics. The real test might come from experiments seeking to detect the resolution of spacetime itself. If the universe is pixelated at the Planck scale, future quantum gravity probes could uncover its digital scaffolding. The simulation hypothesis forces us to confront profound questions, not just about the cosmos, but about consciousness. If we're artificial constructs in a higher reality, do our thoughts and emotions have any inherent meaning, or are they just lines of code in an alien server? It's a modern twist on age-old philosophical debates about existence and perception, blending metaphysics with cutting-edge physics. Whether the theory holds or not, its value lies in the audacity to question reality itself, to wonder if the universe is more than it seems, and if the answers might be hidden in the very glitches we've spent centuries trying to explain. From phantom forces bending spacecraft to galaxies racing toward unseen horizons, these 30 observations prove one undeniable truth: cosmology is a field still brimming with mysteries, each one more tantalizing than the last. Think about it. We've mapped the cosmic microwave background, weighed invisible dark matter, and even glimpsed the edge of a black hole. Yet the universe keeps throwing curveballs that leave scientists both exhilarated and humbled. The Pioneer Anomaly's unexplained deceleration, the Great Attractor's invisible pull, the haunting whisper of the axis of evil in the CMB, these aren't just footnotes in a textbook. They're neon signs pointing toward gaps in our understanding, urging us to dig deeper. Take the Hubble Tension, for instance. Here we have two of the most trusted methods for measuring cosmic expansion, each backed by mountains of data, yet they disagree by just enough to keep physicists up at night. It's like building two identical clocks, only to watch one tick steadily while the other mysteriously speeds up. Or consider the eerie synchrony of dwarf galaxies orbiting in perfect disks, defying dark matter's predicted chaos. These aren't mere statistical flukes, they're cosmic breadcrumbs, hinting at forces or laws we've yet to name. And then there's the grandest question of all. What if these anomalies aren't isolated puzzles but pieces of a larger pattern? Could the Lithium Problem, the missing baryons, and the neutrino mass anomaly all stem from some underlying physics we've overlooked? When you step back, these mysteries form a mosaic of the unknown, each fragment revealing how much we still have to learn. The universe isn't just hiding its secrets in distant quasars or colliding black holes, it's whispering them in the subtle mismatches between theory and observation, in the data that refuses to fit neatly into our models. What's truly thrilling is that we're living in the golden age of discovery. Telescopes like James Webb and gravitational wave detectors like LIGO are peeling back layers of the cosmos we've never seen before. Every anomaly we uncover isn't a dead end, it's an invitation. An invitation to rethink gravity, to question the nature of dark energy, or even to entertain possibilities as wild as parallel universes or simulated realities. The day we stop being surprised by the cosmos is the day we stop truly exploring it. So what's next? Will we finally detect dark matter particles, or will they slip through our nets forever? Could the next gamma ray burst carry evidence of quantum gravity, or will it deepen the mystery? One thing's certain, the universe isn't done surprising us. Whether you're a seasoned space enthusiast or someone who's just beginning to gaze up at the stars with wonder, these puzzles remind us that science isn't about having all the answers, it's about asking better questions. Now it's your turn. Which of these cosmic anomalies fascinates you the most? Do you think we're on the verge of a paradigm shift, or are the biggest revelations still centuries away? Drop your thoughts below, and let's keep the conversation as boundless as the cosmos itself. Don't forget to subscribe and hit the bell, because the next breakthrough could be just around the corner, and you won't want to miss it. Until then, keep looking up. The universe has plenty more secrets